this point, we hope to be familiar with this type of function. It's the absolute value of quadratic, so we're going to kind of get that U-shaped function that's been, part of it's been flipped upside down to give that W shape. Here we want, again, the key idea is we want to find the boundary. So at x equals 2 and negative 2, that's when we're going to get the zeros of the inside function. So we want to know when it's going to be positive and when it's going to be negative. Okay, so if I can do some tests. I know that my parabola looks like this. So I know it's going to be negative in between and positive on the outside. So there's my outside positive and inside negative. Okay, and then I have to account for that +3 as well. But this little picture here is just for my domain. So to find my positive domain, I'm going to be using values less than or equal to negative 2 and greater than or equal to positive 2. That's going to be the domain of the positive parts of the function. So if I can test it, negative 18 squared, yeah, that's going to be positive. So for the positive version, it's going to be y equals nothing changes on the inside, +3, that simplifies to x squared minus 1. So that's going to be my positive version. So I'm going to have x squared minus 1, and that's going to be for the domain from negative infinity to negative 2 and from positive 2 to positive infinity. Okay, it's going to be on the outsides. I then find my negative domain. So the negative is going to be in between 2 and negative 2. It's going to be that region in there. So for the function then, when it's negative, the inside has to flip. To flip it, we use its opposite. So we use, instead of x squared minus 4, I use negative x squared plus 4. And then plus 3. Simplifying that, I end up with an upside down parabola with its vertex at 7, 0 and 7. So that's my negative version. So it's going to be negative x squared plus 7, and it's going to be in the domain from negative 2 to positive 2. There's my domain in interval notation. So then I want to graph this. I know my boundary points are going to be at 2 and negative 2. So I may want to draw a table of values, and plugging in 2 and negative 2, I get my vertex. My shift here is going to be +3. That's not my vertex, sorry. That's going to just be my shift. Okay, so it's going to generate the 0 here, and the y-coordinate is going to be at 3 and negative 3. So there's going to be my boundary points. The positive version is going to be a parabola going up like this. Okay, and my negative version is going to be the upside down parabola like that. Now if I want to draw it a little bit more accurately, I should probably put a few coordinates in, but I should have an idea what this looks like before I graph this. So negative 3, I'm going to end up with positive 4. It's going to be a point here, and it's going to be this parabola shape here. It's going to be symmetrical. And then I'm just going to draw my vertex in the middle. That's going to be from the negative version of this. Okay, when x is 0, I get positive 7 as my y-intercept. And so it's going to be my upside down parabola like this. I think I maybe should draw in a couple more points here because my parabola looks a little funny. So negative 4, I'm going to have positive 7 as my coordinate. Negative 4 squared, negative 4 squared is positive 16, 12, 15. Oh, it's going to be way up there. it's going to be at 15. So I don't think that coordinate's correct. Let's try that again. Negative 3 squared minus 4 is 5, plus 3 is 8. So it's going to be up here. That's why. Okay, so it looked a little funny to me. So it's because that parabola point I graphed incorrectly. So that's not going to be positive 4. Okay, so just double checking that. Negative 3 squared is 9, minus 4 is 5, plus 3 is 8. And so that point's going to be symmetrical at 8 as well. Okay, so there's that's a better looking graph. So there's my graph. So it's drawn in a piecewise function. I have my positive parts in green and my negative part which got flipped upside down in red, and my boundary points were at when the inside is equal to 0. So other piecewise functions, we can draw other piecewise functions based on these definitions here. So we've been given a domain for this set function, and we can be a domain for this part of the function. So I'm going to graph this function, and I'll do it in different colors here. So this is this portion here. Okay, and this is slightly different, that there's the boundary, we don't know why it's being bounded in this region. It's not the absolute value. Before we knew that the bounds were based on the absolute value, but here we don't, these bounds are arbitrary. So between negative 4 and negative 2, we have values. This is a linear function with slope negative 1 and y-intercept of 2. So I'm just going to do a quick table of values here. And really I want the endpoints here. So from negative 4 to negative 2, so I'm going to plug in negative 4. That gives me positive 4 plus 2 is 6. So negative 4, positive 6. And my other endpoint is going to be negative 2. So negative of negative 2 is 2 plus 2 is 4. So negative 2, positive 4. I'm going to graph those coordinates. Negative 4, positive 6. Negative 2, positive 4. And between those 2 points, it's going to be a straight line. And notice that it's not equal to here, so I'm going to have to show that as an empty space. Okay, because it doesn't quite equal that. So that's the positive, that's the green version. For this domain, for bigger than negative 2, it's going to be this parabola. So at negative 2, I'm going to plug in. So negative 2 squared is 4, minus 2 is 2. Okay, so I'm going to end up with negative 2, 2. Now this is equal to, so the point is not going to be on the green line, it's going to be on the red portion of this. And this is a parabola. We have a vertex at 0, negative 2, and we'll just plug in a symmetrical point here. We'll use positive 2 and 2, and so this is a parabola that looks like this and is just going to keep on going. Okay, so this is my piecewise function. It starts here, there's a hole here, it jumps, and it continues on forever here. So is this a continuous function? Well, this definition of continuity is fairly straightforward. Does it break apart? And in this case it does. So this is not a continuous function because it breaks apart. And this issue of continuity is actually an important issue later on. So we want to just make sure that we understand how the basic idea of it. It's actually quite a simple concept, but we want to formalize it. So it's not a continuous function because as we go from the left and as we go from the right, we don't end up in the same spot, so it breaks apart.